Stanford University.
Well, I'm glad to be here. I'll give you a little bit of my take on where I think things stand with the past, present, and future of nuclear power. I'd just like to start off giving you a little bit of a sense of what it is that I do and what I do at the Nuclear Regulatory Commission. So just a couple of slides. You'll notice there's a common theme throughout several of these. In almost every one of these pictures, there's cake. At the NRC, we eat a lot of cake. We celebrate a lot of different things. And at the end, I'll show you one of the reasons that we really celebrate. For those of you who are students and are looking for careers, the NRC is certainly a good place to go. This picture shows you it's not all suits and ties. Every now and then, we actually get to go out in the field and look at interesting things. This is a nuclear power plant. This is the containment structure on a nuclear power plant. And if you look in here closely, there's actually an extremely significant crack that developed in this very thick containment structure that houses this nuclear power plant. And I like this picture because I think it's a good reminder of the unique challenges that we face in the nuclear industry. We've been operating nuclear power plants or overseeing the operations of nuclear power plants for a long time, more than 40 years. And yet we still find new phenomenon. This was something that happened about a year ago, and it was a huge surprise. What they were doing was some construction work, and they have a big concrete structure that contains the reactor itself. And that structure is intended to protect the environment in the event of an accident. And they were doing some equipment replacement, and they needed to cut a hole in this big containment structure. And when they did that, they found this giant crack here. So it's a very interesting issue from a technical standpoint, and it just shows you the kinds of challenges that we continue to work with and deal with at the Nuclear Regulatory Commission. So what is the Nuclear Regulatory Commission? We are 5 commissioners. We're about 4,000 staff, and we are hiring. We're always hiring. We were created in 1954 as the Atomic Energy Commission. Our job at that time was really a combination of different things. It was at a time in which the nuclear industry in this country was developing. At the same time that industry was developing, there was a lot of efforts to develop the nuclear weapons infrastructure and the nuclear weapons complex in the United States. And the Atomic Energy Commission had a significant role in both of those things. And you may think that this is a history in a lot of ways, but the issues that came up with the Atomic Energy Commission are things that are really relevant to today, because we're seeing today in discussions and talk about what's happening in the Gulf about this idea of splitting the regulatory function from the promotional function of the Minerals Management Service, which has the responsibility for dealing with oil and gas leasing. They have a piece that collects royalties and a piece that actually goes about doing the regulations. And one of the things you heard people say immediately after the Gulf spill was, we need to split those functions. Well, that same issue affected the nuclear power industry and the Nuclear Regulatory Commission several decades ago. And it was clear after a series of events that it was necessary to split the Nuclear Regulatory Commission, or at that time the Atomic Energy Commission, into 2 pieces. One of those became the Nuclear Regulatory Commission. The other thing became something called the Energy Resource and Development Agency, or ERDA, which ultimately became the Department of Energy. So there's a little bit of history, but it's also history that's somewhat relevant to today. This is just a little bit of a description of what it is that we do. Ultimately, the NRC is all about our mission of regulating the civilian use of nuclear material. And that basically means 3 things: protecting public health and safety, ensuring the common defense and security, and environmental protection. Now, to do all that, we've got a series of basic things that we do. We do licensing, which means we go through the process of allowing or preventing people from using nuclear materials. We have a program, if they get licensed to use them, where we oversee their use to ensure that it's being done in a safe and secure way. We do research where we need to ensure that the technologies that are being used are used safely and are being used appropriately. the last one there, rulemaking. Rulemaking is all about how the legal and structure that we have. That's how we go about putting our requirements in place, is through something we call rulemaking, which just means pretty much what it says. We make rules and regulations. Incident response, that's where we kind of have our final layer of defense, and we make sure that in the event of some kind of accident that we're prepared and we can respond and deal with that accident appropriately. So that's a little bit about what we do. You know, when I started out, my background was in physics. So I spent a lot of time as a graduate student getting a PhD in physics and learning about a very esoteric property of baryons and mesons and other nuclear particles. And then when I was done with my PhD, I decided I wanted to do something a little bit different. So I went to Washington and got a fellowship. Well, I got to Washington and got a fellowship to work in the executive branch and learned a little bit about the executive branch and tried to pull all my history and American history textbooks and government and civics classes notes from when I was in high school and middle school. So I can remember basically the way the federal government works. And the thing that was most useful to me was Schoolhouse Rock. And there are those of you who remember Schoolhouse Rock, and there are those of you who probably watch it on YouTube. So I think if you have not, you should all check out Schoolhouse Rock on YouTube. These are probably some of the best things that were ever created to teach people about how the government works. And there's one of them that talks all about the three different branches of government, the judicial, the executive, and the legislative. Nowhere in there is a discussion about independent regulatory commissions, which is what the NRC is. So where we fit within this structure, in a lot of ways, we are really an extension of the congressional branch of government. We ultimately report really to Congress. We are an independent regulatory body, and what that means is we're independent of the executive branch decision-making process. So we have our own commission, which has authority to make licensing decisions and other kinds of decisions relative to the material we regulate. And ultimately, we have a reporting requirement and responsibility to Congress. Now, we do have some attachment to the executive branch. The president appoints the 5 commissioners who are then confirmed by the Senate. And then ultimately, the president designates one of the commissioners as chairman, and that's my job and what I do. So what I want to talk to you a little bit about is the past, the present, and I think an insight of mine about where the future of nuclear power is. And all of this from the perspective of a regulator. It's interesting to start with 2 quotes. The first one is a very interesting quote and captures, I think, the nuclear issue in a very important way. It's a quote from Lewis Strauss, who was one of the first chairs of the Atomic Energy Commission, and what he said was, our children will enjoy in their homes electric energy too cheap to meter. This has become known as the too cheap to meter statement. This is often attributed to nuclear power, as the nuclear power energy source would ultimately be too cheap to meter, and at a time when people were working to really enhance and develop nuclear power, they use this phrase a lot. It's also a phrase that's been used by people who oppose nuclear power when nuclear power became very expensive. But as you can see from this quote, it's really more about electricity in general and electrification of our country. And the fact that when we had this massive electrification, it would actually be something that would enhance people's lives because it would ultimately be very cheap and provide electricity fairly cheaply. If we skip forward to 2001, there was a great article in The Economist, a whole issue dedicated to nuclear power and its resurgence, and whether or not it would be resurgent. And they had a great line, I thought, which was, what was once claimed to be too cheap to meter, nuclear power is now too expensive to matter. Well, that was in 2001. The situation in 2010 is perhaps somewhat different. There's a little bit of probably truth in some of the statements in here from The Economist that nuclear power certainly is an expensive energy source. I'm not so sure if today we can say that it's too expensive, though, to matter. And so what I'll talk to you a little bit about is one of the reasons why I think it matters, and that gets into politics. Now, the past. If I look at the past when I think about nuclear technology and nuclear regulation in particular, one of the important things I think that stands out was the development of sophisticated scientifically and technically based tools to do regulation. The early part of the nuclear power industry did not have the benefit of all of these tools. And what I'm going to talk to you about is what are some of the consequences for that. When we get to the present, I'm going to show you a very different picture, which is nuclear power and nuclear power regulation that's done with much more sophisticated tools that I think have provided a much better framework for doing it. And then we'll talk a little bit about what that means for the future. If I look historically at nuclear power, the basic approach to regulating safety were these 5 fundamental principles, namely deterministic. And what we mean by deterministic in a regulatory space is we put very specific requirements on nuclear power technology. So if you're talking about the fuel that powers the reactor, we have very specific requirements about how hot that fuel can get in an accident scenario, or other properties of the fuel, very specifically laid out in our regulations. This idea of single failure criteria is a philosophy that there shouldn't be one element or one activity in the power plant's operations that could cause failure for lots and lots of components. So you want to avoid having something which is a single failure or a single point of failure within your system. Redundancy, very important. That if you have a way to solve a problem or to deal with an accident, you want to have multiple versions of that in case one of them fails. Diversity. Diversity means that if you have a problem, not only do you want to have a way to solve it and redundant ways to do that, but you want to have another completely different way to solve the same problem in case your first problem or your first solution has got single point failure. Because then if you have redundancies, if you've got the same failure in all of those, that's not going to work. So then you need to have diversity. And finally, the last idea or concept that we've got is defense in depth, which means that when we look at safety, we look at all these systems that we've created, and we assume that they fail. And then we look at what do we need to do when one of them fails. And then we look at that system and we say, well, what happens when that fails? What do we need to do next? So you can look, obviously, the issue that's on a lot of people's mind right now is what's happening in the Gulf with the oil and gas industry. And if you look at these ideas, it'd be very interesting to take and at some point compare these philosophies to how we regulate oil and gas. And I would say that, in particular, we're missing these ideas of redundancy, diversity, and defense in depth. So those are important concepts, and they really underlie the framework that was originally created for regulation of nuclear power. Now, in the early days of the nuclear power industry, those concepts weren't fully learned and fully appreciated. So in 1975, we got the first of our really significant instances of operating experience. We had a plant in the United States at Browns Ferry that had a fire. Now, this fire was very significant for a couple of reasons. Number one, it was caused in a very interesting way. At that time, I showed you in the beginning this big concrete structure. It's called our containment. A lot of plants have some kind of structure and way to ensure that, again, in this idea of defense in depth, if you've got an accident and you release materials, you want to contain that material in some kind of cavity so that it doesn't get out in the environment. Well, that cavity then, of course, needs to be airtight. Well, this is a structure like any other structure. It's a big, complicated industrial machine. So you have power cables, you have other equipment that has to go in and out of this structure. So you need to make sure that all of those seals that contain, or the pathways that allow those materials to go in and out, that they're all sealed and that they're airtight. Well, a simple way to test if something is airtight or not, you take a candle or other flame source, and you hold that flame source near the seals. And if you have any air movement, you'll see a deflection in the candle or in the flame. Well, that's in fact how they were testing for air leakage at Browns Ferry. Now, one of the things they didn't think about was that flame could ignite the cables. And in fact, that's what happened. It's a very serious accident. And they had a fire, and they didn't know what to do with it. Because everything they were told at that time was you get a fire, you've got all these electrical cables, and that's what started to burn. And these are power cables that control important equipment in the nuclear power reactor. So what happened was everything they were told was they had water to put out the fire, and you can't put water on live electrical cables. So they didn't know what to do. Okay, those ideas of diversity, of defense in depth, of redundancy, they hadn't yet been fully appreciated in the plants. So they had a significant fire. What they eventually did wind up doing was put water on it, and they doused the fire. And there was ultimately no significant safety impacts from the fire, but it was a significant lesson. And the important point here is that prior to 1975, fire was not treated as a significant issue from a safety perspective. It was looked at more at preserving the infrastructure. So how do we make sure that in the event of a fire, I can recover as the business operator, the owner, the equipment that gets lost? It was treated more as an industrial hazard from the standpoint of ensuring the loss from the event of a fire. And these are just some pictures of some of the damage. As I said, most of it impacted these electrical cable trays, and you can see some of the damage here to these cabling and the power and control cables in the plant. And you can see quite a few areas were affected. So what did we do? Well, we took these ideas of diversity, defense in depth, redundancy, and we put in place new requirements on nuclear power plants. It was not our best effort because it's very difficult to take an existing nuclear power plant and impose a lot of new requirements on the structure, because these are sophisticated, large structures that are very complicated to build and have a lot of components. But it took into consideration these ideas of being deterministic. We put in place very specific requirements. We said that you had to protect one train of safety systems. There always had to be a safety system that, in the event of a fire at the plant, could perform all of its safety functions to safely shut down the nuclear power plant. And we did that in a very prescriptive way. So going back to that idea of deterministic regulations, we said that there's three ways you have to do this. One, you have to make sure that there's 20 feet of separation between those safety trains, so that if one has a fire, you know the other one will stay safe from the fire. Or if you can't have that separation, then you need to enclose one of those safety systems in some kind of fire barrier so that it can last for at least 3 hours. And if that isn't going to work, then you have to have a 1-hour barrier with some kind of way to suppress the fire. So those were the kind of very specific regulations that we put in place after that fire. So that was a very significant piece of operating experience. Again, based on a system that wasn't really looking with a very complex or foundational set of technical and scientifically based requirements for regulation. Two more very significant pieces of operational experience. 1979, 3 Mile Island and the accident there, and then 1986, Chernobyl. Both of these had very important lessons. Certainly Chernobyl didn't have a lot of direct lessons for the United States because it was a very different reactor design, but there were a lot of lessons for us to learn and understand about how people actually go about operating nuclear power plants, or how they do it in a very incorrect way. 3 Mile Island taught us a lot about how we actually go about developing and designing the control rooms where operators operated, but it also told us some good things, that a lot of those safety systems worked. That diversity, defense in depth, the redundancy actually ultimately prevented any members of the public from being impacted by those accidents. So if you take all of that operating experience and you look at the situation, this is just a history of the various stages of licensing for nuclear power plants. The red line here represents all of those permits that the NRC issued to construct a nuclear power plant in this country. Now, there's another line I could have put on here, which was all of the construction permits that we received and were working on, and that line would take you somewhere up here to 200. But you notice there's a significant difference between those permits that we issued, the number of licenses we then issued for those sites that were being constructed, and the number that actually operated. So there's a very significant difference in all of those categories. And you'll notice that the big drop-off happens right around 1979. So you had a lot of plants in the process, and we really kind of settled into a much smaller number following the 3 Mile Island accident. So it showed us that this system that we had in place was probably not the most effective way and the best way to go about regulating. So, what people wanted to try and do was do this in a much more technically, scientifically based approach. So to enhance those ideas of diversity and defense in depth with some more technical rigor. And the very first approach to doing this was something called WASH 1400. This was the reactor safety study and an assessment of accident risks in the US commercial nuclear power plants. This was one of the very first attempts to quantify what the real risks were from a nuclear power plant operating. And you can see down here, just to give you a sense, at that time they quantified the risk of an early fatality from some kind of incident. So you've got motor vehicles here, which is about 3 times 10 to the minus 4 per year. And if you go down here, if you look at the nuclear accidents, with assuming 100 reactors, you're looking at something that's a factor of 10 to the 6th lower than the automobile fatality. So now this was a very crude study. It had a lot of problems. There was a lot of unknowns, again, because it was a very early time in the industry. But it gives you a sense right away that there's perhaps a very different, the numbers are telling you something very, very different than the reaction that you saw in 1979. Now, again, Chernobyl is a slightly different situation, very different reactor design, very different, but very different outcome as well. You had significant fatalities and a very serious incident. 3 Mile Island was a very serious incident, but in the end, there were no fatalities and no radiation exposure that really was measurable. So this was an attempt to start to make the system a little bit more scientifically and technically based. And this was one of the very first approaches doing that. As I said, these numbers are not necessarily terribly accurate, but they give you a sense of the different relative risks. So this idea is the direction that the Commission's now heading, this idea of risk-informed regulation. So not just taking these deterministic kinds of ideas, but trying to take a look at taking this technical information about risk calculations and trying to derive some better ideas about how we can go about regulating and ensuring that we're capturing the right kinds of ideas and the right approaches to safety. I'm going to give you a good example of the difference between a deterministic regulation and risk-based or risk-informed regulation. Take a room like this. A deterministic regulation would say you need to have 3 ways to get out of this room, let's say as an example. So we've got an exit there, an exit there, and an exit there. A risk-informed regulation would say, okay, well, if what I'm trying to do is make sure that people can get out of the room in the event of a fire, then I want to make sure that I have a door and that behind that door there's a path for them to get out into an open space. Okay? So the deterministic regulation would just say have 3 doors. The risk-informed regulation would say it doesn't really matter how many doors I have, but it matters where do people usually go, how much traffic is there when they get out in the hallways, is there a preferred way that people are going to go, and should I try and use that particular approach? So that's a little bit of the thinking. Now that requires very sophisticated tools. You have to know all about the traffic or the pedestrian flow patterns for the particular building you're in. You've got to know what people's behaviors might be in the event of a fire. You've got to know how often you might have fires, how often, all of those different kinds of things. So it requires a much more robust technical infrastructure. So as we get into the mid-'80s, that infrastructure is starting to be developed. So the Commission went about trying to come up with some very quantifiable goals for safety. So we get past this just deterministic idea that we need to just say that there's got to be 3 exits or 3 doors in the room, to saying what it is we're trying to accomplish. And this is what you see here. So there was the qualitative health objectives, which says that individual members of the public should be provided a level of protection from the consequences of nuclear power plant operation such that individuals bear no significant additional risk to life and health. Okay, that's a reasonable kind of statement that I think everybody would agree with. And then as another one, societal risk to life and health from nuclear power plant operations should be comparable to or less than the risk of generating electricity by viable competing technologies and should not be a significant addition to other societal risks. So again, I mean, these are things that I think people would agree are acceptable kinds of goals to have from a safety standpoint. As a regulator, it's not particularly easy to use those. I mean, that's a hard thing to every time you want to make a regulatory decision to have to try and look at these things and analyze them. So the Commission came up with some more qualitative health objectives, which try to put these things into numerical perspective, which would be useful as we do more and more calculations. And you can read these here. Probably the interesting thing to think about these is that in this case, they're all relative to some other kind of risk. So for instance, the risk to an average individual living near a nuclear power plant of prompt fatality. So that means in the event of an accident, you would receive such a large radiation dose that you would die from that dose. That should not exceed 0.1% of the sum of prompt fatality risk resulting from other accidents to which members of the population are generally exposed. Now, an interesting thing to keep in mind here is if we reduce all the accidents, then you've also got to reduce or increase the safety of a nuclear power plant to keep in that relative risk perspective. Similar here, the risk to the population in the area of a nuclear power plant of cancer fatality. So those would be the kinds of impacts you would have over longer periods of time. So if there was a radiation release and that release didn't instantly, was not large enough dose to cause an immediate death, it might at some point later increase your risk of getting cancer. So that's what this second metric tries to capture. Again, keep in mind that's relative to the risk, the overall risk of cancer. So it raises an interesting question. If cancer rates societally go up, does that mean we should do less for nuclear power regulation because those relative risks have increased? And similarly, if we eliminate cancer or really reduce the risk of cancer in all other areas, should we similarly try and work down, in particular, with nuclear? So this was an attempt to try and get a much better framework for how we go about doing it. Now, ultimately, what the agency uses today is we've taken this one, and we've broken it down into two things that we measure. One is the risk of the core of the reactor melting, and the other is the risk that if the core of the reactor melts, you're going to get a large release in a very short period of time of radiation. So that ultimately captures these two concepts, but in a way that's a little bit easier for the agency to work with numerically. So following that, having that safety goal, the Commission then went back to look again and try and come up with another sense of what is the risk really from these nuclear power plants. So we did really the second significant risk study at the nuclear power industry, and that was something we call New Reg 1150, and that just refers to the NRC document that we have. And this was a study of 5 different plants to get a general sense of where they fall in this risk perspective. So by 1990, the tools and the technology have advanced significantly. And we now have a better way to try and understand what is really significant at a nuclear power plant. You know, is fire a real significant event? And it turns out that fire is a significant event. Fire tends to dominate the risk for most nuclear power plants when you look at these numbers, something that we didn't understand before Browns Ferry. And you can get a sense here just of where the numbers, if you look at this NRC safety goal, this is kind of an extrapolation, as I said, from those safety goals you saw on the other page. You'll see that a typical plant will be several orders of magnitude below those safety goals. So it turns out right now, it looks like most of the plants generally do a little bit better than where we think those safety goals are. So that's a little bit of a sense of kind of that next level of study that we did about nuclear power plant risk. So the Commission then said, all right, now we've got this new tool. It's a very valuable tool, right? The ability to do these computer models that look at risk, look at probability, but we had this original model, which was based on these ideas of very precise rules, defense in depth. How do we marry these two things together? Because it's clear we can't completely go to the computer-based approach and just the numbers, because as good as those programs and systems may be, they have limitations, as any modeling does. Right? And a nuclear power plant is extremely complicated. So to model that is a real challenge, and it continues to this day to be a real challenge. So the Commission didn't want to throw out everything we had before, but they also didn't want to forget this really powerful new tool. So the Commission came up with a policy statement that talked about how we're going to bring those two things together. And that was a 1995 policy statement that we produced. And the really important piece of this, and PRA just stands for probabilistic risk assessment. So these are the computer tools that give us these risk calculations. And basically, this is the most important piece of it. the use of PRA technology should be increased to the extent that's supported by the state of the art in the technology. So we shouldn't use computer codes that can't be used for the things we're trying to use them for. And it has to be done in a way that complements what we've already done. So this deterministic approach to safety, the defense in depth, all of these ideas that were really there at the beginning, and that when 3 Mile Island happened showed that they worked. Because in 3 Mile Island, all the additional redundancy worked. It ensured that there was not a release of radiation to the public. So we don't want to throw away some of the things that we have, but we also realize there's some new tools and new ways to do things. So this is the way the Commission goes about doing its work now, and tries to focus its work on more of these kinds of things. So the past was about learning and understanding that we needed better tools and we needed more sophisticated ways to do it. So where did that leave us? What do we know today? Well, today, we're now talking about a very different situation. 2001, I showed you the slide that said what was once too expensive to matter, or too cheap to meter is now too expensive to matter. That was 2001. At the beginning is these ideas of implementing these risk-informed regulatory concepts. So today we have 104 operating nuclear power plants. We have applications for 22 new plants in this country. We have 4 designs that we've approved that would incorporate a lot of these new ideas. We have reviews for 5 other new designs that are currently underway at the NRC. We have proposed designs for new kinds of power reactors, so-called small modular reactors. We have the Department of Energy providing loan guarantees to support the construction of new nuclear power plants. And we have the cost for a single nuclear power plant being about $6 to $10 billion. So, you know, there's a couple lessons you can draw here. It's that this high level of safety and security is not cheap. But it's something that, because of these changes in the way we've gone about regulating nuclear power plants, the nuclear power plants in this country have become a lot safer. And they've become safer to the point where people are now talking about the potential for new nuclear power plants in this country, which is a far cry from where we were 10 years ago. Now, as a regulator, I don't have a particular interest one way or another, but the reality is things have changed. There is now a discussion at the political level in Washington and within Congress about potentially having new nuclear construction. So this is just an overview of where some of the plants are. The colors are just reflective of actually which part of NRC regulates them. They don't have any significance other than that. And you'll see that a lot of the plants are here in the northeast, or in the northeast of the U.S. A lot clustered here in the southeast, some here in the Midwest, and then sporadic in the west and here on the West Coast. Another aspect that came out of this improvement in safety and improvement in the technical infrastructure is we took those 104 operating plants that we had and we effectively added about 6 new plants. Because what we did was we had licensees come into the NRC and they wanted to make changes to their plants. They said, you know, we started out with this system that was deterministic and that put in place all of this redundancy. And we now have very sophisticated tools and models, namely this probabilistic risk assessment tool. And using those tools, we can find out where we've over-designed and over-engineered the nuclear power plants. And so what they came to us with were approaches to increasing the power of the nuclear power plants while still maintaining the safety that they had experienced over the last 10 or 20, 30 years. And the only way we could do that was by marrying up these two concepts of this deterministic basis, which ensured safety, and then this risk-informed tools, which allowed us to better define what was really most important for safety, and in some cases find that there were things we could do to the plant that would allow greater operation, but would still preserve the high degree of safety and security. So you see here that we've added almost 5,700 megawatts of electric power from the existing fleet of reactors. That's the equivalent of having built almost 6 nuclear reactors in this country. So while we didn't build any new plants, we were effectively adding new nuclear generation in this country, or the industry was. And the NRC was going through and making sure that in each of these cases, the plants would still maintain the high level of safety that we had ultimately force them to achieve. So these are just some pictures of some of the work we do to make sure that these plants do continue to operate safely and securely. Now, if you look at the situation going forward, here's where we are today. We have, as I said, 13 applications for 22 new reactors, and you'll notice that most of them tend to be down here in the southeast and in the southern United States. That's where we anticipate right now, if we have new plants licensed in this country, that they would likely, the ones that would likely be constructed earliest would probably be down here in the southeast. It's not likely right now, although we may see a few plants in the northeast, it's not likely that we'll see a lot in the northeast right now. That's just a little bit of the situation. So you can contrast that with the slide here of the general distribution of plants right now. We're seeing much more interest in nuclear down here. So why is that? You know, we started off, I think, with an industry that, and a regulatory framework that wasn't as sophisticated as it needed to be. And we had situations like the Browns Ferry fire, where we had not fully understood that fire was a significant contributor to the kinds of problems that have an ultimate impact on the safety of the public. So we learned from that. We then got more sophisticated with our tools, so we didn't have to use things like the Browns Ferry fire as a way to learn. We could run computer models that would tell us, you know what, here's a particular problem. If you have an earthquake, here are the systems you want to make sure are protected, and if you don't, these are the kinds of consequences you're going to have. So we could run those models and get a good sense of what's going to happen without having to deal with it in the real world. And that's what we never want to do. So we were able to put in place a much more technically rigorous way to regulate nuclear power plants. And the result has brought us to where we are today. The interesting thing about the future, I'll talk about that. Oops. The interesting thing about the future is everything I said probably doesn't matter. The future of nuclear power in this country will probably be what it's always been, which is a very political debate and discussion. And you know, I showed you that very first slide about Lewis Strauss talking about too cheap to meter, and that's always been associated with nuclear power. It's one of the issues with nuclear power. It's one of the things that makes it such an interesting area in which to regulate, because there is tremendous public interest in nuclear power. There's strong opposition, there's strong proponents for nuclear power and advocates, and there's these two forces that are always almost at battle. And one of the places where that battle comes to a head is in the United States Congress. There's been a lot of work done by the NRC over the last several decades to put in place a system that I firmly believe makes nuclear power plants safer than they've ever been. And it's a system that allows us to focus our resources in the right way, and it allows us to work with licensees to make sure they focus their resources in the right way to make sure that these plants stay safe and secure. The future of nuclear power in this country will probably hinge more than anything else on what Congress decides to do about climate change and about regulating carbon. I showed you that one slide several slides ago, which showed the price of a new reactor is anywhere from $6 to $10 billion. That is a lot of money. It's not a lot of money that, or it's not the kind of money that anybody on Wall Street is willing to lend to a utility, and it's not the kind of money that a lot of utilities right now are willing to put up on their own. Most utilities in this country, if they're publicly traded companies, do not have a market capitalization that is greater than $6 to $10 billion. In other words, if they were to build a nuclear power plant and it was not a successful endeavor, they're banking the company on that endeavor. So there's not a lot of companies that are interested in actually completing and doing the construction. But the one thing that likely would change their interests is if Congress were to put in place a price for carbon. Because under a lot of scenarios and modeling that's done, if there's a certain price for carbon, it makes nuclear a more favorable option for utilities to consider to meet electricity needs. Now, as a regulator, we're not necessarily concerned one way or another about that. I just have to make sure we're prepared to deal with the workload if, in fact, something like that materializes. So I think there's been a lot of good work that's been done over the last several decades to change dramatically the way we regulate nuclear power. And I think one of the things that you'll see in the next several months is people will start asking about this when they start dealing with the Gulf. And as I said, you've already seen some of that discussion. I've seen newspaper articles that talk about the split of the Atomic Energy Commission. And that needs to be repeated for the Minerals Management Service. I heard somebody, a member of Congress, I think just last week, said we need to do a 3 Mile Island type commission to study what went wrong in the Gulf. Those were things that we did 30 years ago. And now people are learning, I think, and looking to the Nuclear Regulatory Commission and how we regulate to see how we can take that system and apply it to other industries and other safety-sensitive areas in parts of this country. But the future is ultimately going to be, I think, shaped fundamentally by what happens with climate legislation. If climate legislation happens, there'll be a price for carbon. It will probably make nuclear more cost competitive, and that $6 to $10 billion may seem more palatable to some utility executives relative to the cost of other types of generating sources because of the price now that carbon would impose. So fundamentally, that's what this debate is going to come down to. And I think it's interesting because the one issue, as I look at the debate in Congress, that seems to be the bargaining chip, if you will, is nuclear. And it's the one issue that Democrats are using to try and get Republicans to support climate. It's the one issue that Republicans who support climate legislation are holding out on to get Democrats, or holding out on climate in order to get support for nuclear from Democrats. It's the one thing that's right in the middle. And in the end, what it comes down to is having a good, solid regulator. And a good, solid regulator like the NRC. Because if we don't ensure that the current fleet of operating reactors are safe, if we don't ensure that our licensing process ensures that new plants that might be built are built safely, then there will be no nuclear expansion in this country. It's really that simple. So the work that the people at the NRC do every day is vital to this nation. It's vital because we have that responsibility to protect public health and safety. And so for those of you who are students and are interested in a career in government, let me tell you what your future could be. The U.S. Nuclear Regulatory Commission is one of the best places to work in the federal government. We, in a survey 2 of the last 4 years, have come out first out of 250 other federal agencies. We are among the best-in-class ratings. We were the #1 large agency in the rankings, the #1 for strategic management, the #1 for effective leadership. Now, some of this happened before I was there, so I can't take credit for that. #1 for work-life balance, #1 among African Americans, #1 among Hispanics, #1 among women, #1 among employees under 40, and #1 for paying benefits. So I'll let that slide speak for itself. Thank you very much. Sure.
Okay. All right. Okay. Questions. Yeah. Why don't we start back over way in the back with the orange shirt?
Sure. Talk a little bit about what's going on with Vermont Yankee and how you expect that regulatory process to unfold.
Well, for those of you who don't know, Vermont Yankee is a nuclear power plant in Vermont. It's an older, relatively smaller design. Now, I can't talk too much. There's some things I can't talk about, but I'll give you a general overview. One of the things I didn't talk about, but I could have easily showed you a slide about, is a process we call relicensing. Nuclear power plants in this country were licensed for 40 years of operation. The Atomic Energy Act, which is the statute that governs our behavior, says that plants can come in for relicensing and get an extension on their license. So about half the fleet of reactors have come in for approval of these relicensing activities, and the NRC has granted approval in many of those cases. Some of them are still undergoing review. Vermont Yankee is one of those. So I can't talk specifically about our sense of where that is because it's in a formal hearing process that I can't get into the details about. But I can tell you a little bit of the situation there. As part of that process, now, getting a nuclear power plant license in this country is predominantly about getting a license from the Nuclear Regulatory Commission. But it does also involve other federal and state agencies. And the way that many states operate, in order to have any kind of electricity generating source, whether it's a gas plant, whether it's coal, they have to get approvals from state regulatory bodies. that are economic regulators. So that they ensure that utilities are charging appropriate rates and all of those kinds of things. So they need those kinds of approvals. Well, in the state of Vermont, there's a lot of opposition in the state government to granting those approvals that the state would have to give in order to allow the plant to operate beyond its 40-year period. So right now, if the NRC were to extend its license, it's possible the plant would not operate because it wouldn't get the approvals that they need from the other state agencies that are necessary. So right now, it's unclear what will happen. I think if you look at the way they've structured the situation in Vermont, it requires their legislature to affirmatively agree to provide what they call a certificate of public good, which is that statement that, yes, this is in fact in the best interest of the state from an economic regulatory perspective to have this plant operating. They need their state legislator to affirmatively provide that. And they had a vote 6 months ago and resoundingly rejected providing that approval. But it's something that they could keep trying to get. And I have enough trouble trying to predict where the United States Congress will come out. I'm not going to try and predict where the state legislature in Vermont will come out. But right now, if this were to be the last vote, and they affirmatively need to grant this. So if they never vote again, then they would not get that certificate, and then the plant would not continue its licensing or its operation.
Yeah, I have a question. You do have some control over. Last year I learned that I think it was TVA had 3 upgrade applications submitted in 2005, and one of them was granted for an increase, and 2 more would not be addressed until 2012, which indicates you have a staffing problem. This is also related to it takes on average 44 months from COL to approve. What can you do to expedite that process in light of the need for carbon-free power?
Well, maybe I'll start with, sure, I'll repeat the question. The question was about Browns Ferry, which is a nuclear power plant, and some requests for power uprates, and that we've approved 1 and haven't approved 2 others. And that was a result, I'm paraphrasing, that was a result of staff, it would indicate we have staffing challenges, and then that the licensing process takes 40-some months, and what can we do to streamline that? I'll start with the first one. The situation with the power uprates with Browns Ferry is not a staffing shortage problem at the NRC. The power uprate that was done at Browns Ferry involves some technical issues that were poorly understood by the industry, and it also was at a time when Browns Ferry was doing a lot of different things. They were also trying to relicense all 3 of their units, as well as bringing a 3rd unit that had been shut down for a long period of time back online. So if there was a staffing problem, it was really actually more with the utility. They were not able to provide the right kind of technical work that we could review on a timely basis.
Or a nuclear news report.
Sorry?
Incomplete nuclear news report.
Yes, so I would not characterize it as an NRC staffing problem. There was a technical issue there, and what we granted was a limited uprate for 1 of the units, and for them to demonstrate that that will be done safely, and if so, then we would do some of the other units, or they would come in for the approvals on the other units. The issue of the time it takes to do a licensing is a very interesting one. It's probably a good place for me to use my favorite analogy. I always talk about this, and the analogy I always use is getting your college degree, or maybe even a PhD is probably a better example. When I went in to get my PhD, I got a PhD in physics. I was shooting for about a 5-year track. Now, I did theoretical work, which I think is a little bit more predictable sometimes because you're not relying on experiments that sometimes don't give you the answers you're looking for or break or whatever. So I got done in about 5 years. And the licensing process is a lot like that. People come into the process, they have aspirations about when they want their licenses, but to get them, they have to do certain things. like if you're getting a PhD or a master's or a bachelor's, you've got to go to your classes, you've got to complete your problem sets, you've got to pay attention, you've got to pass, you've got to get good grades. Well, we have those same issues with all of our applicants. And right now, I would say that most of the applicants that have come in early, the first kind of movers in this process, did not necessarily have the right level of completion in their applications and did not have the right level of quality for us to be able to review them in a timely way. So that's created, and that's natural, and that's not a criticism. It's, the best analogy I could use would be, say, it was the first person who ever went to college. It was a little bit of an unknown process, how you get through and how you get done. And expectations, it takes time to figure out, well, what's the right level of coursework and all of those things. Well, the process we're using is slightly new. So it's an old process, but it's never really been used this way. So it's a little bit more involved, I think, than the applicants expected. Now, in terms of, though, the process being more straightforward, one of the things that the commission did in the 80s was they changed the process. And so the old process basically, you constructed the plant first and then you came in for your final regulatory approvals. Well, the way the process works now, you come in for your final regulatory approvals before you go on and do construction. So there's more certainty on the back end. The other thing the commission did when it changed that process was it put in place a way to get designs approved without, irrespective of whether or not somebody had a site where they were going to build a plant. So that the thinking was that you would go in, if you were interested in a nuclear power plant, and you would look at one of these designs that had been approved, you would take that design and you'd take your site and you'd go and you'd send us an application that said, here's how that design is going to work on this site. That is a much more straightforward way to do licensing. Right now, what we're in the process of doing is both of those things simultaneously. The designs that most of the applicants are looking at are designs that have not yet gone through the design approval. So that is the most technically complex and the most challenging part of the review, and it's really the piece that's driving the length of time that it takes to do the licensing. So we're having to wait to make decisions about licensing until we get to the finalization of some of these design issues. So in terms of the process being better in the future, there's two things that need to happen. One, we have to get the applicants to give us all the information we need to complete these design reviews and make our safety determinations. Two, the applicants in the future, if we do approve these, and we've approved others in the past, so there's a likelihood we'll approve some of these. The second thing is that the applicants have to actually use them. There's nothing in our regulations that says they have to use these approved designs, but if they do, it makes for a much more efficient process. Now that, if any of you, you buy a car or whatever you buy, or bicycles, I like to ride bikes. Every bike manufacturer every year comes out now, or every 2 or 3 years comes out with a brand new bike. And road bikes these days are, they're lighter than pretty much anything else you can think of. And yet every 2 or 3 years they come out with a newer and better version. Well, they charge more money for it, and that gives them an excuse to raise the prices or whatever the case may be. But it gives you a way to buy. Now, for a typical rider like me, I'm not going to notice the difference in any of those bikes. And probably even most pros these days don't really even notice the difference between any of these bikes, because the ironic thing is they make them so light now that they have to add weight to them because they're too light for the regulations. So we're moving this direction where we're getting all this better and better technology, but it's not really of use to anyone. Well, the nuclear industry can have suffer from that same failure, which is that there can be a desire to make things better and better. Whenever they want to change something about a design, they have to come to the NRC to get approval. So if we've approved a design, we think it's safe, and we have a pretty good idea at this point of what safety means. If it meets that standard, from an NRC perspective, we don't need to see additional design changes. And if vendors and the applicants are disciplined, they won't want to make changes either. If they do, it's going to create additional regulatory work for the 5th, 6th, 7th, and 8th reactor that might want to be built in this country. So the most important thing for this system to work is for the applicants to be disciplined. And the history is that they're not. I showed you we have 104 operating reactors in this country. We have about 80 designs. Although in principle, they're really only 6 or 7 actual designs. Every time they built one, they hired a different architect and engineering firm that said, well, we can build that design cheaper and better if you make this modification and this tweak. The end result is we've got all of these designs, and they're all very unique. So from a regulatory perspective, it's a lot more work. We have to do a lot more to train our inspectors to know and understand the differences. They have to do a lot more work to train their operators to know and understand the differences. And it's just not a very sustainable system. So the idea was to have this design approval process to get standardization. But in the end, it's up to the private sector to decide whether or not they want to do that. But I can tell you it will be a lot more efficient from a review standpoint if they follow it.
Okay, we'll take one more question. How about you?
Do you have some idea of what would happen to the relative risk of the nuclear industry in general if reprocessing of spent fuel started happening again, or is that something that you would say?
We, in terms of what the safety implications would be, or what the impact would be in the future of the industry.
More like what would happen to the safety implications.
It's well, there's 2 aspects. Reprocessing is the process of taking the spent fuel that's been used and then separating out fissionable materials and remaking fuel from it. So there's 2 real safety issues there and security issues. Well, there's 3. Let's say there's 3. The first and foremost is the safety and the security of the actual process, that reprocessing process itself. There's the current process that's used and used relatively effectively in France and in Japan now is a well understood process. It does involve some degree of it creates a lot of liquid waste products that can be difficult to manage. So if it's done right, it can be done effectively. There's a facility in the UK which is an example of how it's not been done well and has a lot of significant environmental contamination issues and other problems. So that issue is one that we haven't really addressed in this country in a long time. We had a facility in New York that was built to do reprocessing. It's a facility that we're continuing now actually to do decontamination and cleanup from the process. So the NRC doesn't really have in place the requirements right now for what it would mean to do it safely. It's something we're looking at doing, but it's not the top of the list of things we do because reprocessing not probably, at least in the next 10 years, not likely to happen. The second thing to think about then is if you're going to reprocess, the whole idea is you take this material and you make new reactor fuel. So there's a safety issue there that we need to analyze if that reactor fuel, which is slightly different than the reactor fuel that's used now, can that operate safely and securely in a power reactor? That's actually something that we're looking at right now and analyzing because there is an attempt to make this kind of fuel using surplus weapons grade plutonium. It's so-called MOX fuel or mixed oxides. So you have plutonium and uranium in the fuel. So that's something we have pretty good information right now that says that we think that can be done safely, and it's something that's done safely in other countries. The third issue really is what you do with all the leftover products, the very sensitive radioactive material, or the very highly radioactive materials that are left over from the reprocessing process. And that puts you pretty much back to where we are with most of our high-level waste, which is we ultimately need a strategy and a direction nationally for what we're going to do with that material in the long term. So that piece is probably not as well understood, but right now we have a good sense that certainly the spent fuel itself can be maintained safely and secured for at least 100 years. And we would have strategies to deal with that high-level waste that comes out of reprocessing, probably in a similar time frame.
Okay. All right. Well, thank you very much.
Sure.
For more, please visit us at stanford.edu.